everybody, in this talk I'll be presenting Switch V2P, an in-network caching solution for address translation in virtual networks. This is joint work between the Technion and University of Michigan. Physical networks are structured, so physical IPs provide both the location and identity of physical servers. This structure allows for an efficient compression of the forwarding rules in network switches. In contrast, virtual networks decouple the physical and virtual IPs, so virtual IPs are only identifiers for VMs, but they do not provide any location information. While this decoupling gives flexibility to tenants and operators, those also management costs. Senders must get the virtual to physical mapping of the destination to allow the network switches to forward packets. For example, in this topology, we have two VMs and two machines. The center VM creates a packet with the inner addressing header that includes virtual IPs. The hypervisor can then include the outer addressing header with the physical IP. While the sender knows its own IPs and the virtual destination IP, it still has to consult the V2P mapping database to find the physical location of the destination VM. In addition, the virtual IP address space is dynamic and frequently changing. One of the main challenges in the address translation is maintaining consistency despite frequent updates. These updates occur due to VM migrations, initialization instructions of new VMs, and the dynamic nature of tenant activity. This brings us to an important question. Where should we perform address translation? As a very basic and fundamental problem, many solutions have been proposed mainly by big hyperscalers. They can be classified into two main categories: host-driven designs and gateway-driven designs. In the host-driven design, address translation is performed at the servers. This design offers fast routing performance because the translations are done close to the source. However, it suffers from slow updates, especially in large networks. When mappings are changed, updating all the relevant hosts can take seconds in large networks and tens of milliseconds for a single server to get new mappings. This places substantial load on the control plane and, during the inconsistency window, on the all destination server as well. On the other hand, in the gateway-driven design, a dedicated set of gateways handles address translations. Senders send their packets to these gateways, which resolves the address and relays the packets to the destination. This approach provides fast updates because translations are centralized. However, it comes at the cost of slower routing performance and increased network bandwidth usage because packets have to go through the gateway and the way to their destination. This may create a bottleneck, and it is especially severe when there are insufficient number of deployed gateways, which may lead to packet drops. From a distributed computing perspective, these approaches fall into the two extremes of the read-write trade-off. In the host-driven design, replication factor is high as mappings are replicated across many machines, but updates are slow because there are many replicas to update. On the other hand, centralized gateways are fast to update, but slow to read from. And the basic solution to this trade-off is very clear, right? We just need to limit the replication factor. In that way, we can balance the update and read costs. But what is the right middle ground in virtual networks? To escape this trade-off, we propose Switch V2P, an in-network address translation solution. Switch V2P enhances the gateway-driven design by caching V2P mappings within programmable switches in the data plane. Switches are designed to manipulate packet headers and forward packets, so they can do that efficiently. Therefore, this approach ensures both fast routing performance when there is high cache hit rate and fast updates because there are an order of magnitude fewer switches than servers in a fat-free topology. Switch V2P also allows cache entries to be shared among different racks and pods, so it can also reduce fast packet latency. And as I'll show you later in this talk, Switch V2P does not make packet detours during the lookup process, so we never lose performance. Now, let's get into the details of how this solution works. In Switch V2P, each switch acts as a gateway and maintains a cache with a subset of the V2P mappings. Let's see an example to understand how it works. First, packets are sent to the gateway as before because in the beginning of the run, all the caches are empty. The gateway can then resolve the address and send the packet to its destination. So on a miss, we follow the gateway design. However, on a cache hit, the switch already has the required V2P mapping, so it can directly modify the packet headers and forward the packet to its destination. This bypasses the gateway, resulting in faster packet delivery. Note that we do not change the routing in this process, so packets do not take any detours during the lookup process, so routing overheads are never increased. The goal obviously is to maximize the cache hit and minimize the need for gateway involvement. Now we need to decide how to admit new entries to the cache. In switch V2P, switches learn by observing traffic. There are two opportunities to learn mappings. As packets flow through the switches on their way to the gateway, switches can learn the mapping of the sender. This is very similar to how MAC learning works. Similarly, when packets are relayed by the gateway, switches can learn the mapping of the receiver, and this dynamic learning process ensures that the cache adapts to changing traffic patterns. While caching in switches offers significant benefits, it also presents challenges. Switches have limited compute and memory resources, making it very difficult to implement complex cache policies and data structures. Having large data sketches to find popular mappings can be helpful in deciding which mappings to cache, but on the other hand, it also consumes memory, so it reduces the cache size. Popular cache policies like LRU can be expensive and impractical in the data plane, so therefore we need to design efficient caching mechanisms that can work within these constraints. On top of these challenging characteristics of the switch hardware, there are also several key challenges we need to address. First, we need to ensure that important mappings are kept in the cache, while less critical ones can be evicted. To do that, we use a topology-aware caching mechanism that can be implemented efficiently in the data plane. Second, when mappings are updated, the cache may contain incoherent mappings. Despite that, we need to ensure that packets are always forwarded to the right destination. To address that challenge, we introduce lazy invalidations. To give you better intuition on why this problem is challenging, let's take a look at an example where each switch performs destination learning and takes local decisions. Again, in the beginning, all the caches are empty, and packets from V1 to VM2 are sent to the gateway. When the gateway forwards the packets to VM2, switches on the path from the gateway to VM2 can learn VM2's mapping. However, we can immediately see several problems with this approach. First, VM2's mapping is replicated in irrelevant switches, which won't be used again. Second, the gateway switch is expected to experience high turnover of entries, so VM2 mapping may be evicted before the next packet from VM1 even reaches the switch. This will lead to another cache miss and increased packet latency. Finally, this design does not even consider the topology. Entries may be replicated at multiple switch levels, although mappings at the upper levels should only maintain popular entries that can be shared among multiple racks of pods. To deal with these challenges, we introduce topology-aware caching. Switches use a direct map cache with minimal overhead. Tor switches learn source addresses, gateway tors learn destination addresses, and switches strive to keep mappings in the cache, so when they evict an entry, they try to speed it to another switch. Popular entries are promoted to upper levels so they can be shared among multiple senders. And finally, gateway tors generate learning packets, which aim to keep important mappings in the network and move them to where they are needed. This is a very informal description of our algorithm, so I encourage you to take a look at our paper for more details. So let's see how this works through an example. Here, VM1 communicates with VM2, and as packets flow from VM1 to VM2, the Tor switch learns VM1's mapping. Switches can also learn VM2's mapping on the path from the gateway to VM2. In addition, VM1's mapping is learned via source learning. Finally, The gateway Tor generates a learning packet, allowing the sender Tor to learn VM2's mapping, so the next packets can be directly sent to VM2. Now, VM3 communicates with VM4. Packets are sent to the gateway as before. VM3 mapping is learned via source learning. VM4's mapping is learned on the way from the gateway to VM4. However, due to a collision, VM2's mapping is evicted from the gateway Tor, but is kept and spilled to the next spine switch. Finally, thanks to learning packets, the next packets can be sent directly to VM4. On that path, VM4's mapping is promoted to the core switch as well. Now, when VM1 communicates with VM4, packets are sent to the gateway but hits the cache on the array, so they can be directly sent to VM4. Finally, when VM3 sends packet to VM2, it can utilize VM2's speed mapping at the spine switch. Now, let's talk about updates. When a VM is migrated, the switch may hold stale mappings, which will forward packets to the wrong place. Instead of invalidating the caches in the network switches, we allow the cache to be incoherent and lazily invalidate it, so we won't flood the entire network. First, we need to make sure that packets are forwarded correctly after migration. When a server receives a packet for a non-existing VM, it uses the default rule and forwards the packet to the gateway. Tor switches can then detect misdelivered packets because they know physical IPs of directly attached servers. When a packet with a non-matching IP comes into the Tor from a downlink, the Tor then detects a misdelivery. At that point, the Tor tags the packet and forwards it to the gateway. Other switches on the way can then invalidate their cache entries and forward the packets to the gateway. As a result, packets will be eventually forwarded to the right destination. Although background traffic may evict stale entries, packets may be sent to the old destination indefinitely. Therefore, the Tor also generates an invalidation packet to explicitly remove the stale entry. This is done by a special tag that switches use to note where the cache was hit in the topology. Then the Tor can use that tag to know to which specific switch it needs to send the invalidation packet. To evaluate our approach, we run large-scale simulations on the NS3 simulator. We use a large fetch tree topology with 10,000 VMs and 80 switches, and we also use typical data center workload traces. We report both network and application level metrics. And these are our main results. We show that we can significantly reduce both flow completion time and first packet latency. We show that we can achieve very low miss rates, so we can get the same performance with an order of magnitude fewer gateways. And as a result, we also reduce the network load because packets can be sent directly without entering the gateway pod at all. Finally, we also show that we can handle updates efficiently. We compare switch V2P against several baselines. No cache is a pure gateway approach. Gateway cache adds a cache in switches that are directly attached to the gateways. Local learning is the greedy approach that I described earlier. Direct assumes that mappings are pre-programmed, so packets take the shortest path to the destination. And finally, in on-demand, only the first packet in the flow goes to the gateway, and next packets are sent directly to the destination. Also, the mapping is cached on the host, so other flows can reuse it again. In the next two slides, I'll show you our results for the Hadoop workload. This graph shows the hit rate for each baseline against switch V2P, so higher is better. On the x-axis, we vary the cache size. Values are in percentage and are relative to the address space size, which is 10,000. A 1% cache size for switch V2P means that each switch has one entry. We vary the cache size from 1% to 1,000% because on the one hand, 80 switches can keep that many mappings, but on the other hand, in practice, these spaces share them among different address spaces. This graph shows that Switch V2P performs better than the other baselines. It can reduce the load on the gateways even with a single cache entry, and with a 10% cache size, it achieves a hit rate of about 70%. This graph shows the flow completion time improvement normalized to no cache, so again, higher is better. We can see that although gateway cache and local learning achieve similar hit rates for large case sizes, Switch V2P outperforms them because it can place mapping closer to the center, thus it reduces the path that packets take. In addition, Switch V2P also outperforms the on-demand baseline because it allows effective sharing of cache entries. Finally, Switch V2P reduces the flow completion time by a factor of 7.8 compared to no cache. We also evaluated an in-cache scenario in which 64 senders communicate with the same VM. Then we migrate that VM to a different physical machine. All the numbers in the table are normalized to no cache. We can see that because control plane updates are slow, there are 11 times more packets that reach the old destination on-demand. On the other hand, with only 24 invalidation packets, Switch V2P reduces that number significantly while keeping the same average packet density. In conclusion, Switch V2P empowers switches to perform in-network address translation. We introduced a topology-aware caching policy and an efficient solution for updates. Switch V2P is practical and efficient, and also significantly improves both network and application level metrics. Thank you for listening.